Hi, everyone. So today, this is our first part of the integral videos. We've got integral part 1 and integrals part 2 coming up next. So let's start first. What is an integral? So an integral is basically a backwards derivative, right? A derivative is like finding the slope graph of a curve. We will talk about graphically what is an integral. How do you find the not slope, right? What is the reverse of a slope graph of a curve? But in calculus terms, an integral is basically the function that if you were to take the derivative of it, you would get your original function. Whoops. So we have, let me show you that real quick. So normal calculus notation for this is if you have f prime of t, right, and you take the integral of f prime of t dt, then you would get your original function. And this original function, if you took the derivative of it, you would then get f prime of t, right? So that's kind of our quick down and dirty. That's what we're going to call an integral in this class. We're not going to get into a deep discussion on what is an integral. That is more of a calculus class discussion, but we're also going to use pretty basic integrals in this class. We're not going to do anything super complicated or fancy. It's going to be the anti-power rule, basically the power rule backwards. And then we'll talk a little bit about how to get a natural log, just because we've already used that in this chapter before. So number 2, right? Number 2 asks, how does this enhance our ability to calculate work, or sorry, to solve for position, velocity, and acceleration? So if we look at what we know so far, right? Let's zoom in. We've got position, velocity, acceleration, and even beyond that, we have jerk that we have talked about before. And if you take the derivative of these, you can move down the ladder, right? That would be the derivative. Now, if you want to take the integral, right? If you take the integral of these functions, integral of jerk becomes acceleration, integral of acceleration is velocity, integral of velocity is position. So it basically allows us to move back and forth pretty fluidly between all of these different concepts. Now, we also have the concept of integrating over time. For example, impulse is something we will talk about later in this class. This is shown by a capital cursive I. You have a force versus time graph, and impulse is usually shown as some spike in force. And what we can do is we can take the integral from this time to this time to find out what was that impulse, what was that surge of force in that small amount of time. Impulse is usually running on small amounts of time, like milliseconds, for, say, a ball bounces off a wall, right, or a boxing glove hits a chin. Really quick contact, but a big surge of force. Impulse actually describes that surge in force over that small period of time. So you can integrate over that time to figure out what the impulse would be. All right, another example of integrating across something would be work. Now, work shows force over distance. So if we have another graph, we have force over position, right? And if we say that we are applying a force over this distance, if we take the integral of work, say we want to find out how much work was done from the starting point up to that position there, we can integrate force across this distance from some S1 to S2 to find out how much work was done on the object during that during that motion. And work is shown by this W here. That's the symbol we will use for work. But that is all next chapter. But that's what integration allows us to do. It allows you to identify, let's integrate from 5 seconds to 8 seconds and see how much impulse was there, or integrate from the 3 meter mark all the way to the 8 meter mark and how much work was done in that motion. So that enhances our ability and gives us another tool in our tool belt as we are trying to mathematically work our way through physics. Now, number 3 asks, write down the anti-power rule that is used for simple integrals. So the anti-power rule, this is basically the power rule backwards, right? You have the integral. This is the integral symbol. It's a big curvy S. So you take the integral of this function with respect to this variable. So you have your function there. Then the dx is telling you integrate the x variable. Now, if we integrate x to the n dx, instead of subtracting 1 from the exponent, bringing exponents down and multiplying, we actually do the opposite. We will add 1 to the exponent, and instead of multiplying, we actually divide by that exponent. Now, here's a new part. We also add a constant. Remember, in derivatives, if there is any constant that doesn't have a variable, it's 0. You take it away. Well, here, remember, if we are trying to figure out what function, if you take the derivative of it, gives you the other said function, there could be a constant there. We have no idea because it could have gone to 0. So you need to add this plus c to your integrals, because it could be there, it may not. We don't actually know that. There are other steps to find your constant if you have a certain amount of information. And we'll go over how to do that in a minute. But there might be a constant there, so you always need to put plus c on an integral like this. This is called indefinite. An indefinite integral gives you the function of said integral, right? Or of said, yeah, you know. Indefinite integrals are also, they don't have these bounds, right? Where we said over here, like an impulse, if you go from one time to the next, or work from one position to the next. That's not indefinite, that's definite. We'll go over that in a minute as well. But this is what an indefinite integral gives you, okay? Real quick, I also want to say that if you have the integral of k times x to the n dx, and if you have this constant k multiplying there, you can actually take the k out of the integral and work your integral the same way. So then you would just have k on the outside, and that will multiply by x to the n plus 1 over n plus 1 plus some constant c. Right? So we can also show, if, let's see if I have room. If we take x to the n plus 1 over n plus 1 plus c, and we take the derivative of it. Okay, whoops. We take the derivative of this. What this will actually give us is it will actually take us back to x to the n, and I'll show you that. Let's rewrite this as 1 over n plus 1 times x to the n plus 1 plus c, right? And then we will take the derivative of this function. Now, to take the derivative, you take the exponent and you bring it down, so then you have n plus 1 over n plus 1 times x. Then you decrease the exponent by 1, so n plus 1 minus 1 is n. Then a constant becomes 0. Then n plus 1 over n plus 1 is 1. So you return to x to the n. So this just shows you that if you take the integral and then the derivative, you can just bounce back and forth. That's one way to check your work as well. All right, so that's a quick introduction to the integration we're going to be doing in this class. Now, graphing integrals. What does this look like graphically? Well, graphically, a derivative is finding the slope, right? You find the slope of a graph, and that gives you the the derivative graph. But what an integral means graphically is you are actually finding the area under the curve, right? But if you want to find that algebraically, that's really difficult, right? Just like finding the slope at given points across a graph, that kind of tedious and takes time. Well, as you can see here in this picture, you can start off, when you do this, you can start off with squares, rectangles and triangles, and then you can move on to trapezoids that more closely fit the curve of your graph. But that's not as efficient. As you can see here, this is area under the graph that you're missing. This is area under the graph that you have overshot. And then here is more, you overshot there, you missed that area, you missed that area, you overshot big time here, missed that area, overshot there. So all that red is error in trying to estimate this geometrically, right? And when you get into some complex equations, you can actually get really close on finding the area under a curve without any calculus. But calculus makes the process easier, right? So that's what the integral means graphically. Now we want to talk about a definite and indefinite integral. We already talked about indefinite, right? Indefinite is when you have the integral of x to the n dx with absolutely no bounds, right? Well, a definite integral means that you put some bounds on that. So let's say we want x to the n from x initial to x final. So then that gives us x to the n plus 1 over n plus 1 plus, oh, you don't even put the plus c. That's from the value x naught to xf. This little show right here tells you, it's just a different way of saying this function from the bottom value to the top value. And that's what that means. So if we do this integral and we're going to solve it, we take final minus initial, which we do all the time in physics. You take xf to the n plus 1 divided by n plus 1, then you subtract the initial, x naught to the n plus 1 divided by n plus 1. And this is going to give you a value, not an equation. So that is a major difference between indefinite and definite integrals. One gives you an equation, the other gives you a set value because you're trying to find the actual value of whatever you're trying to find. Say we're just looking at the impulse, right? We talked about impulse before. Say we're looking at what was the impulse from a set time to another set time, from t initial to t final. You want a number to give you an answer to the impulse. If you just want an equation, then you would take the indefinite integral. But if you want a value, take the definite integral. The definite integral also does not include the constant c because you're finding a direct value. You don't need the constant c when you're doing that. All right. So that is the difference between definite and indefinite integrals and what it looks like to graph an integral. Now we've got some practice problems. I'm going to run through these real quick. The first two are green. That means that we usually do these in class together. The third one being red means that you need to do it on your own. That doesn't really work on a video. So once we get to number 3, I'll ask you to pause the video, try it on your own, and then go from there. So let's work on number 1. Number 1 first. We have dy dx, which means the derivative of some function x with respect to y. That equals 3x to the 4th minus 8x cubed plus 3x plus 5. We want to find what is the original equation, y of x. So we will use the anti-power rule. Anti-power rule works with very basic polynomials. If you have polynomials divided by polynomials and you've got fractions, it actually gets kind of complicated. But if you can break it down to a simple polynomial, anti-power rule can work. So we will take 3x to the 5th over 5, just add 1 to the exponent and divide, minus 8x to the 4th over 4. We can see that that's going to go to 2. Then you've got 3x squared over 2 plus 5x. Now here's the trick. When you take the integral of a constant, you actually add the variable to that. You don't add the variable, right, strictly mathematically. You combine it with that variable, right? In derivatives, you take away the constant. Here, you give that constant a variable, and then you put a plus c on the end of that. So if we were to rewrite this simplified, you could say that is 3/5 x to the 5th minus 2x to the 4th plus 3/2 x squared plus 5x plus c. There you go. Okay. So that's how you can do the anti-power rule with that one. Next, let's do number 2. We have y prime, which just represents the derivative of y. That equals 3t squared plus 4t. And we're given the information that y equals 2 at t equals 3. Now, let's find the original function y of t. Well, we have 3t squared. That becomes 3t cubed. Whoops. 3t cubed over 3. That will cancel there. Then you have 4t squared over 2. That cancels there to a 2. Then you have plus c. So if we rewrite that, we get t cubed plus 2t squared plus c. However, remember when I said that you can actually find the value of c if you are given the information necessary. Here, we have new information. This isn't something we've had before. So at t equals 3, that means the function y equals 2. So if we set all these t's to 3's, so you've got 3 cubed plus 2 times 3 squared plus c. Now we can actually solve for c. So that would be 2 minus 3 cubed is 27. 2 times 3 squared is 18. So that will come out to equal negative 43. So, and that is our constant c. So we can now put that back into our function. We have t cubed plus 2t squared minus 43. All right, now that's how we can do those first two. The third one, if v of t, the velocity function with respect to time, equals 6t squared plus 4t plus 3 meters per minute, and if s equals 40 meters when t equals 1 minute, find the function s of t. So go ahead and pause this video, solve that on your own, come back and I'll work through it. Okay, so we have 6t squared plus 4t plus 3, and s equals 40 at, what was it, t equals 1. So now we want s of t if that is v of t. So remember, solving the integral for velocity can give you position, whereas the derivative of velocity gives you acceleration. So let's solve this integral real quick. We have 6t cubed over 3, that'll cancel. You've got 4t squared over 2, that'll cancel. I guess simplify, not cancel, right? Then you've got 3t plus c. So let's rewrite that real quick. 6 over 3 is 2. Then we've got another 4 over 2 is 2. So we've got 2t cubed plus 2t squared plus 3t plus c. And s of 1 equals 40. So that would be 2 times 1 plus 2 times 1 plus 3 times 1 plus c. Solve for c, you get 40 minus 2 minus 2 minus 3 equals c, which would be 33. So our function s of t would equal 2t cubed plus 2t squared plus 3t plus 33 meters. And when it gives you that information, right? When you have this information, minutes per meter, you have meters, you have minutes, you really need to include your units on that function. If the units are given, your correct answer is going to also need units. So make sure that you are giving your units when you solve that kind of equation. All right, that's all we have for the first video of integrals part 1. Integrals part 2 will be coming next, where we do a couple more integral practice problems.